Hi, I'm Japan from UC Berkeley. I will be talking to you about how to predict whether a given initial path is good enough for trajectory optimization. Trajectory optimization is a powerful tool for motion planning and has been used in many robotics applications, including ladder robot locomotion, grasping, opening a door, and humanoid locomotion. Given an initial trajectory that may collide with obstacles, ideally, the trajectory optimization algorithm should be able to generate a feasible and collision-free path. Compared to other motion planning approaches, trajectory optimization has several advantages. First, it can scale well to high degrees of freedom problems. Second, it can tackle complicated constraints, such as dynamics constraints and joint limit constraints. Third, the trajectory computed by optimization is locally optimal, which is helpful for many applications. And finally, trajectory optimization is often faster than other planning approaches. However, trajectory optimization also has limitations, of which the most important one is that the optimization process may not converge to a collision-free trajectory, as shown in this example, where the optimization is trapped in an in-collision local optimum. Before we go into the details of the trajectory quality prediction, let's first discuss some background on trajectory optimization. This approach optimizes a trajectory, let's say, robot joint angles of time. We don't want joint angles to change too much from time t to time p plus 1. There might be some other costs that you care about, subject to in the start state at time 0 and within a goal state at time capital T. The trajectory should satisfy joint limits. Moreover, for all robot parts and for all obstacles, you want no collision. That is the non-convex and hard part. And the solution method proposed in the RS 2013 work by Zhuo et al. Handles this through sequential convex optimization. Then how does it work? Well, there is a very efficient way to compute the standard distances between two convex shapes. They are the JJK algorithm and the EPA algorithm. They compute the standard distances, meaning that what is the minimum distance two objects have to move to get into collision or to get out of collision. Based on the standard distance, we can make a constraint that the standard distance must be bigger than 0, meaning that there is no collision. In the sequential convex optimization approach, we need to linearize this collision constraint using the Jacobian matrix, and then the linearized constraints can be used in the inner loop of the sequential convex optimization approach. Intuitively, you penalize more and more when two objects are getting in collision. The outer loop of the sequential convex optimization will make this penalty steeper and steeper. One thing in the optimization is that you don't want the robot to jump through obstacles. You want to make sure that from time to t to t plus 1, you keep track of the volume that is swept out by the robot links and make sure that the entire volume is not in collision. It turns out that the JJK EPA algorithm that we rely on to do collision checking can achieve this about equally as fast as just collision checking for a static object, just a factor of 2 slower. An upside here is that overall, we might to sample the trajectory more costly, so you might actually have a speed up thanks to the overall. Overall, it can be faster because it tends to make for a better convex optimization problem, because you now look really at the shape of the trajectory rather than the discrete samples along the trajectory. So overall, the optimization tends to be best behaved, and overall, it tends to require less iterations than when only performing discrete time collision checking. One of the properties of planning algorithms like RT and A star is that asymptotically, if you continue to refine your discretization or you keep sampling, they are guaranteed to succeed, though it may take a long time, too long for practical purposes sometimes. However, the optimization approaches don't have such guarantee, so the way to evaluate them is through benchmarks. You set up a set of test cases, both realistic and of interest. Here are two example benchmarks: a robot around a bookshelf or in a living room, and give goals and start states and see how often this approach succeeds and how long it takes. So we did that. We call it trade-off the algorithm we implemented that I just described. BIRT star, that is the main component here, is considered as the state-of-the-art implementation of RTs, and is part of the OMPR library. The third column is Trump, which is another trajectory optimization algorithm proposed by CMU. We have success rates that is reasonably high for all approaches. It's the highest for trade-off. Trade-off also works faster, and the resulting trajectory is optimized to have the shortest length. For full-body case, our algorithm tends to work quite well over a wide range of the tests. For Trump, the not available does not mean that the algorithm is not applicable, just meaning that the available software is not applicable to this test case. We also applied this to high-dimensional motion planning. 34 degrees of freedom for humanoid, a beam picking test for industrial robot, and planning with non-holonomic constraints, such as needle steering. In this paper, we want to first predict the effectiveness of a given initial pass, meaning that when using this pass as initialization, whether the optimization algorithm will converge to a collision-free feedback trajectory. This is important since trajectory optimization may fail in many cases if the initial pass is not appropriate. For instance, as shown in figure A and B, when the initial pass passes through the middle axis of the obstacles, the gradient computed for optimization algorithm is based on penetration depth or distance field, and may push the trajectory waypoints in inconsistent directions. When a robot collides simultaneously with multiple obstacles, as shown in figure C, the robot may also get stuck in an infeasible local optimum, since different obstacles will push the robot in different directions. Similarly, for a robot with multiple links, as shown in figure D, the optimization will also be trapped in an infeasible local optimum. In order to avoid these failure cases, the trajectory optimization needs to be able to select a good initial path from a set of different initializations. In other words, given a set of initial passes, we need to predict whether each of them will converge to a collision-free path or an inclusion path. There are many previous works trying to solve similar problems. Trajectory prediction approaches by Joseph and Torsent speed up movement generation using knowledge of the successfully optimized movements. Gathering such data allows to create a mapping between the situation and an initial path that is likely to quickly lead the local optimizer to converge to a good movement. Dragon et al. Focused on selecting a good trajectory goal configuration from a set of possible goal configurations that is likely to yield a good trajectory based on previous experiences. It has not yet been extended to consider obstacles, which play a very important role in determining a feasible trajectory. These two methods do not provide recovery methods when the prediction fails, though it is good to have a sequence of initial trajectories as fallbacks so that we can eventually obtain a successful prediction. Recent work by Ross and Day leverages the modular function optimization to order the initial trajectory candidates in an optimal way, such that the trajectory optimization algorithm is more likely to compute a feasible trajectory. Whenever a given initial trajectory is not appropriate, and the optimization algorithm cannot find a collision-free path, we can pick a new initial path from the ordered set of initial path candidates until a collision-free path is computed. In order to predict the influence of an initial path on the optimization convergence, we choose not to directly learn the knowledge from trajectory joint values, because in this way it is difficult to involve environment-related features, and the resulting prediction is difficult to generalize well among different environments. Instead, our approach first designs a set of trajectory features and then compute feature vectors for the training set of initial passes. For each initial pass, we run trajectory optimization to determine whether a collision-free path can be generated. Next, we run a two-class linear classifier on these initial passes, which is then used to predict the effectiveness of new trajectories in unseen environments. Now we introduce the features we designed for this purpose. Feature design is more an art than science and is based on various heuristics. The basic principle when designing trajectory features is that the local environment around the trajectory is critical for the convergence result of the optimization algorithm. For instance, here, the red initial path is deeper inside the obstacle than the green initial path, and this implies that the green path is more likely to be a good initial path than the red one. Based on this basic principle, we design 4 different types of features, and I will introduce them one by one. The first feature is called the spatial assigned distance vectors. To compute this feature, we first quantize the space around a robot link according to different directions. In this example, we subdivide a 2D space into 12 parts by using 12 directions B0 to B11. Here, the blue part is the robot link, and the brown color denotes the obstacles. Along each direction, we can compute the maximum distance the link could move, but we are not collide with any obstacles near that direction. For instance, along direction B11, the maximum distance the robot link can move is illustrated as a red arrow, and at that distance, the robot will contact with one of the obstacles, where both the robot and the obstacle are marked by the red polygons. Similarly, we can compute the distance vectors along all the directions. After collecting all values in all directions, we make the feature vector, whose dimension is equal to the number of quantization directions. The second feature we use is called the spherical harmonic spatial features. This feature is rotation invariant, which means that if we rotate the benchmark, this feature will keep unchanged. It is computed by applying spherical harmonic transform on assigned distance features. In particular, given the assigned distance vectors along various directions, the corresponding spherical harmonic transform coefficients makes this feature. The third feature is the difference between spatial and assigned distance vectors. This is used to measure the consistency of obstacle pushing directions. That is, whether obstacles near a robot link were pushed in the same or similar directions. This feature is composed by 2 parts. First is the dot product of the assigned distance vectors between adjacent robot links. The second is the dot product of assigned distance vectors between the same link but belonging to adjacent trajectory waypoints. The final feature is called the convexity features. This feature is used to quantify the level of approximation happened in trajectory optimization. Our trajectory optimization algorithm involves a non-convex objective and non-convex constraints. These non-convex terms are approximated by convex functions in each step of optimization. Convexified features are used to measure the roughness of these convexified steps. In particular, we compute the Hessian matrices of objective and constraints, and then compute the minimum, maximum, or summation of the Hessian matrices eigenvalues. These numbers are collected together as trajectory features. As a prerequisite for learning the predict for the success of an initialization, we need to prepare the training set and the test set. In this paper, the data is collected on different benchmarks, including Dubin-Scar, PR2 arm planning, and full-body PR2 planning. For each benchmark, we generate different planning tasks by selecting different start and goal conclusions for the robot. These conclusions are randomly chosen by Dubin-Scar, but are manually selected for PR2, so that we can have sufficiently many successful trajectory samples. The dataset of trajectories are obtained by different perturbations of a linear trajectory, connecting a pair of initial and goal conclusions. Moreover, all the intermediate trajectories generated during the trajectory optimization process are collected in the dataset. After all the trajectories are collected, we use half of them for training and the other half for test. In order to make sure that the test set and the training set are independent, we make sure that all the perturbations of the same task are either in the training set or in the test set, but not both. In this result, we compare 3 different methods. The first is the baseline algorithm. That is, we predict the trajectory label according to the label of the majority trajectories. The second is our method, using the full set of features. The third is also our method, but not using the convexity feature. From the results, we can see that our method outperforms the baseline significantly, and the full set of features provide the highest prediction accuracy. The convexity feature is relatively expensive to compute and requires 8 seconds for each trajectory. All other features are much cheaper and can be computed in less than 10 milliseconds for each trajectory. Our method still has several limitations. The first, the learned classifier can be different for each benchmark. Second, the predictor calculated on one benchmark is difficult to be transferred to other benchmarks. According to our experience, the transfer is successful only when the benchmarks are similar to each other. For instance, we can transfer the predictor learned on one Dubin-Scar benchmark onto a different Dubin-Scar scene, and still can obtain more than 70% prediction accuracy. For future work, we would like to adopt better trajectory sampling approaches to cover the entire trajectory space. We also need to design new features, including high-level attributes of the environment and trajectory, in order to make the learned trajectory predictor transfer among different benchmarks. Finally, it will be useful to integrate our method with trajectory ranking algorithm. Thank you.